Hi there, I hope you're having a great day. In this video, we'll be taking a look at the LD preload directive, what shared objects are and how to make shared objects in Rust, and what are some of the things we can achieve using shared objects. So to begin with, the line of thought for this or the preface for this video is whenever you write an application, you've got your instructions, right? So if this is the control flow, you've got all of your instructions, and then at some point you have to perform a kernel operation. So essentially, the task of a kernel, so if you've got your kernel, which is Linux or Windows, depending on which operating system you're on, is to sit between the user and the hardware. So you've got your network in here, you've got your file system in here, you've got your input and output devices in here, all sorts of hardware, and your kernel essentially sits between them, and you've got your applications here, and whenever they need to interact with the hardware, they don't directly interact with the hardware, they go through the kernel passes you onto the network or the file system or the IO. Now the interesting part here is the kernel is going to be different depending on your operating system. So if you're using Windows, you've got the Windows kernel. If you're using Linux, you've got the Linux kernel. If you've got Mac OS, you've got something that's based off of BSD, I believe. Anywho, so as an application developer, it's a little tiring to have to deal with all of these kernels. So what ends up happening is you never actually directly interact with the kernel. You never actually perform system calls on the kernel. You have a layer in the middle, which actually abstracts away the application for you. So essentially, it's going to give you a fixed set of APIs or methods that you can call, and that middle layer is actually going to convert it onto the commands that are suitable for the kernel that you're running on. And almost 99% of the time, this middle layer is going to be libc. Even if you're running in a JVM, the JVM often interacts with the kernel through libc, and libc actually handles all of the abstraction of the kernel methods and everything. So the ability that we have for exploiting, not exploiting exactly, but to use libc to our advantage is as follows. Libc is a dynamically linked library. What that means is you can have a million different apps running on your server or on your device, and they all share one common libc, which is dynamically linked. So the libc itself is not part of your application. It resides somewhere on the user's machine, and all of your applications essentially load it in dynamically whenever they need to perform, whenever the application is loaded into memory. So the cool thing about that is at some point in your application, you're going to perform a kernel call. So for an example, if you're going to perform a connect, right, with some address, you're going to perform it, or you could perform an fopen to get access to a file or whatever, any number of syscalls that could be performed through libc. Now, since libc is actually on the user's machine, it's dynamically linked. The ability we have here is to, instead of whenever this kernel call occurs, instead of passing the control on to libc, you could pass it on to your code right here, and your code could either modify the request to libc and then pass it on, or it could straight away perform an early return back without actually giving the control over to libc. This can be achieved by actually performing certain linker directives. That's when LD preload comes in. LD preload is an environment variable. Excuse my terrible handwriting, but LD preload is an environment variable where you can force certain libraries to be put onto the stack. So to give you an example, let's take a look at curl. I'm going to go into, for example, we've all used curl. It's a very common library. If we look at the path at which curl is located, so My curl binary is right here. So what I can do here is I can just call this method, this command, which curl. Right. So LDD essentially lists out all of the binaries that are in use by a particular executable, all of the dynamically linked binaries. Similarly, I can check Python, and Python, it doesn't load as many libraries dynamically, but it's still got a fair bit of libraries that it does bring in. Now, these binaries expose certain methods, and these methods are loaded in the order of precedence. So, for example, if you've got your connect method, it's going to get looked, it's going to be searched for in libcurl. If it's not present there, it's going to go into libc, then libc, and so on and so forth. So, if we are able to inject our shared object at the top, we can essentially override all of these. We can override any method that's present in any of the libraries that come after in the LDD directive. So to give you an example, I'm going to, I've got an LD, I've got a shared object right here somewhere. Let me check. Right. So in here, shared object, I've got one CD target less CD release. Great. I've got the shared object right here. The .d is a shared object that can be used in macOS, and I believe if you were to compile this on Windows, you'd get a .dll that you could use in Windows. But as far as Linux is considered, we're going to use this .so shared object. If I check the file type on this, libsharedobject.so, it's an ELF binary. Anywho, so let's take a look at this. If I was to call curl once, let's call Python for now. Let's check at the libraries that Python uses. That's Python 3.12. We've got these libraries. Let's add in our LD preload directive. That is libsharedobject.so. Great. Now that I've added that, you can see that the libsharedobject.so is actually added to the top of the binary tree. The first one is a Linux shared object, so we cannot override that. But the important part is that our shared object is now at the top. Anywho, so what now? So an example, if I look into the libc, if I decompile libc, let's take a look at this. Let's do an obj dump of this file, and let me pass that into less. You can see that we've got a connect method here somewhere. There we go. There's a connect method that glibc offers that can be used to actually perform connections to any remote object, or when you, or even if you're connecting to localhost, it's going to go through the connect method. That's the libc connect method. You can get the documentation for that in here, man connect.to. So you've got the documentation for the connect method that actually creates a network socket and lets you communicate over it through a file descriptor. This particular shared object that we were looking at also has a connect method. So if I perform an object dump of that, object dump -d libsharedobject.so, we're going to bring that into less. We can see that it's got a connect method as well. And this connect method is exposed to all of the applications that use this library, and it can be it can override the connect method that glibc exposes. Great. So okay, we've talked a lot about a lot of things, but I don't really see anything cool yet. So let's take a look at that. Let's change that. If I do a curl at google.com, I get a response that I expected. I get a 301 moved from google.com. And if I do a curl on the router I've got running, I get this output. So what the output is does not matter. The thing that matters here is that all of my when I perform a curl on google.com, the request actually goes to google.com. And when I perform a curl to 192.168.1.1, I get this response. Now, if I was to add an LD preload directive and point it to the shared object and then do a curl on google.com, you can see that I'm getting the output that I was getting when I was curling 192.168.1.1. So what this LT preload directive, what this LT preload shared object has essentially done is it has overridden my request for google.com with 192.168.1.1. I could enter any arbitrary address over here. For example, 168.0.1 or .2, anything. I could even enter youtube.com, for example, and it would take me to 192.168.1.1. So what has essentially happened is LD preload has intercepted the call to google.com and overridden it with 192.168.1.1. In the same way that we were describing over here, when this connect command is called, my library, instead of letting it, so the command has been called with google.com or the IP behind google.com, and my library has passed it on to libc with 192.168.1.1, and then libc has returned the file descriptor appropriately. So we're going to be building this, and we're going to be looking into how you can build this in Rust and what the caveats are, what the and essentially handle all of the things that we taking a look at all of the things we can achieve with this. And now, even though the video is regarding a networking parameter, a networking method, this is applicable for absolutely anything that's in libc. You can override the connect directive, you can override f open, you can override time. So when the application requests a certain time, you can override that. That essentially lets you mock the time on the application. So when the application checks for system time, instead of it being the date today, you could set it to a date 100 years in the future or 100 years in the past. So that opens a lot of avenues for testing if you're testing an application. Along with that, there are certain nefarious uses for that. For example, if you've got an expired license, although I don't recommend that you do it, but it's something that's possible. If you've got an expired license, you can essentially change the time for one application while the time for all of the other applications remains the same. So all of this is pretty cool. What are the catches? One major catch is that although a lot of applications use libc, there are some applications that use a library called muscle, especially with Rust. And muscle is a library that is statically linked. So what does a statically linked library mean? In a statically linked library, instead of each application referring to the same libc that's on the user's operating system, the entire interface, all of this is actually bundled along with the application itself. So it's in the application binary itself, which means the control is never coming out of the application. So for such use cases, you will not be able to override any of the libc directives because it's never calling libc. Another caveat is when it comes to using the JVM. Most JVMs use libc, whether it's your Temurin JVM or your OpenJDK JVM. However, GraalVM has some issues. I'm not exactly sure. I've not tried anything on GraalVM yet, but I've heard that GraalVM has some issues because it does not perform calls through libc. It has a statically linked library that it performs all of the OS translation on. So that's something to watch out for. But anywho, let's get right into it. We are going to create a new Rust project. So let me open this up, and I'm going to go into a fresh directory. Let's create a directory. You know what? Just do cargo new. I'll call it an interceptor. I'll call the project interceptor, and it's going to be a binary. So, okay, my bad. It's going to be a bin. Great. So I can go into the oh, I spelled it incorrectly. You know what? rmrf intercept cd interceptor, and let's load this in Rust. Beautiful. So now that we have this, I think it messed up the binary directive. That's fine. Let's get rid of this. We're going to create a Rust file called lib.rs, and I am going to get rid of main. Cool. Now in our Cargo.toml, we're going to have to make a few changes. So the first thing is, since we're overriding some of the methods of libc, some of the functions of libc, we're going to need to import libc. As for the version of libc that we're using, we can just copy this, libc 0.2.170. Okay, that is not what I was expecting. Dependencies. Okay, and one additional field that we need to add over here is we need to give the hint to the Cargo compiler or the Rust compiler that our output has to be a library that can be linked with C. So for that, we are going to make it we're going to let it know that crate type is a cdylib. So dylib essentially means it's a dynamically linked library, and C is for, well, we're making it for C. Cool. Now that we've got this going, let's create a new file real quick and call it interceptor. Now in here, we can expose any of the methods that a C library might expose to override them. So let's take a look at the man page for connect. So man connect. We're going to override the connect method. So I'm going to copy this, and let's take a look at the documentation right here. So we're going to override this. So let's copy this as it is and bring it in here. Now all of these variables, the cint, sockadder, socklen, and cint, have to be imported from libc. So let's do that real quick. Libc, and we need cint, sockadder, and we need socklen d. Cool. So now that we've got this going, we need to add a directive called no mangle. I'll explain why we need to add this very shortly, but let's just bear with me for now. And we can return -1 just so that the compiler stops yelling at us. So for now, let's just print whenever a connection is attempted. Let's just say connection attempted, and let's compile this. Cargo build release. Great. Let's go into the target folder, and as you can see, we've got a libinterceptor.so. If I was to decompile it and look at the library look at the assembly behind it, dump -d libinterceptor, pass that into less, you can see that we've got a connect method over here, exactly in the same way that the connect method was for libc. If I was to not add this no mangle and build this again, you can see that I no longer have the connect method. That's because the Rust compiler actually converts the names of methods into something that it can use internally, or it inlines the functions in order to save space on the binary. So to prevent all of that, we have to add the no mangle directive so that it's actually exposed as the method that we called it. Anywho, so once we've built this, let's take a look at where we're at with the example that we had looked at earlier. So I'm going to do a curl to google.com, and as expected, I get the 301 moved. Now what if I was to add the lt preload directive and add the libinterceptor.so and perform a curl, and we get nothing. Cool. We get nothing. However, we have this output that says connection attempted that comes in from here. So at this point, we know that, you know what, we've exposed the method properly. We're able to actually get the println in here. Now let's expand on this a little bit. We'll go one step at a time, all the way until we are able to override the actual address. So let's now that we've got this, let's start with just printing the IP address and the port that is being accessed. Now, if you see over here, we've got a socket address, and we can take a look at the documentation for man connect. Sorry, we can do man connect and take a look at the documentation. And as you can see over here, it says that when you perform a connection, you're going to get the file descriptor. You're going to get a pointer to the address that the connection is to, the address that the connection is to, and then the sock len. Let's take a look at what the sock adder really is. The sock adder, I believe, it's right here, or just we can just go in here. So the sock adder is an abstraction. It could be a sock adder in, or a sock adder in 6, a sock adder in, or an in6, or any number of types of sockets. So if we take a look at the man socket, so the man page for the socket in the C library, we've got a bunch of types. What we're interested in right now is the where is it? Right here. It's the AF inet and the AF inet 6. So AF inet is for the IPv4 sockets, and AF inet 6 is for the IPv6 sockets. So like it says over here, it says that the size of the sock adder structure depends on the type of the sock adder. So for an IPv6 sock adder, you're going to have a larger structure. For an IPv4 sock adder, you're going to have a smaller structure, because it's just for it's a 32-bit address versus the 128 bits for an IPv6. So let's take a look at how we can get around to that. So let's come back in here, and the first thing that we need to check is that we need to make sure this is not this pointer does not point to a null object. So let's do an if not address.is null, and we're going to do all of our bring in all of our logic into this if block. Now that we know that this address exists, we can actually check which kind of a family it is. So let's just call it address type. Address type equals address dot let's take a look inside here. It says SA family T right here, right? And it's a U16. So let's do an SA. Okay, so since this is the pointer to a sock address, we need to perform a pointer dereference. Let's do that. Address and then SA underscore family. SA underscore family, yeah. SA underscore family, and we're going to convert this into an integer. So it's a relatively trivial process to convert it into a C integer. The reason we're converting it into a C integer is because in the man page for socket, all of these enums regarding the type are actually C integers. So we can compare that. I'll give an example. Now we can check, we can perform a match on this. We can perform a match on the address type, and the address type could either be an, just a second, it could be a libc AF inet or a libc AF inet 6, or it could be anything else. So in the case of getting some unexpected address type, let's just throw a panic unexpected address type. Cool. Whoa. These are constants, which are, for example, AFINet is 2 and AFINet 6 is, I believe, 10. Yeah, it's 10. And essentially, we're comparing what kind of an address is in use over here. It's the same thing that was displayed right here. So this is a 0, AF Unix is a 0, AF local is a 1, AFINet is 2, and so on and so forth. It's an enumeration. Anywho, so now that we have the address, we can convert this sockadder object, sockadder structure into, we can essentially upcast it into the relevant address type. So let's take a look at how that's done. We need to convert this sockadder address into either a sockadder IN if it's an IPv4 address, or a sockadder IN6 if it's an IPv6 address. So let's take a look at how we can do that. Let's convert it this way. So I'm going to call it let adder underscore in equals, so we are going to dereference address as a sock adder underscore in. So we are going to, even though when we got this reference in the beginning, it was a sock adder, but we're letting Rust know, you know what, I am aware that we got it as some other object, but I want to convert it into a sock adder underscore in. And this is an inherently unsafe operation. Since it's a raw pointer dereference, it is unsafe because Rust can't predict statically at compile time whether you are performing an appropriate dereferencing. But that's fine, because the aim with building shared objects in Rust is to have all of the parts that have to be unsafe in a relatively small part of your code base, and then you can move all of your business logic, all of your additional logic into other parts of your code which are safe, which are verified by the borrow checker, and which have the memory safety guarantees that Rust offers. Anywho, so let's get the IP out of this. If we take a look at the sock adder, this is a this has got a syn adder field, which is an IP address, which is a 32-bit integer, which is appropriate because an IPv4 integer is 32 bits. So we're going to get that in, and let's get the port as well. So the interesting thing here is all network related numbers are in big endian ordering, and you have to convert that into little endian if you're on an x86 architecture, because x86 generally uses big endian, little endian. So let's do that. Let's do u16 from big endian, and while we're at it, let's convert this to little endian as well, to le. Okay, so now we can just print our address here. Attempting to connect to, we can enter the IP address and finally the port. So let's do that, IP comma port. Great. So we've got this. Let's just copy all of this over into the IPv6 part as well. However, there will be a lot of differences in IPv6. So the first things first, it's a sock adder underscore in6, because an IPv6 address inherently takes a larger space in the memory. So it's going to be a different object altogether. Let's import that as well. And all of these will now change to syn6. Cool. Let's do syn6 here. Let's make this a debuggable output. Cool. Now that we've got all of this, we've got an IPv6 address as well, and we're not doing anything with the connection. We're just printing. We're returning an error, but we're printing the connection, the IP that the user is trying to connect to. So let's build this real quick. Cool, we've built this. Now let's perform the curl again. And as you can see, so my application first attempted to connect via IPv4. When that didn't work, it fell back to IPv6 and it tried to attempt to connect to Google's IPv6 address on port 80. This is a binary representation of the IPv4 address that Google is using. To illustrate this further, let's try to perform a connection on my loopback address for IPv4. And the same thing for IPv6. Let's do a -6 and we're going to do a loopback. So it tried to connect to both of these, IPv4 and IPv6, and we have the answer here. All right, so we've intercepted all of the network connections. Now, how about actually modifying these connections and performing changes accordingly? So to take a look at that, let's go further and actually modify the address into 192.168.1.1 like we had done in the example at the beginning. So for that, I am going to create a new address. It's going to be a mutable variable, which is going to, again, it's going to dereference, it's going to be a reference, sorry, to address. At the beginning, we're going to use it as a reference to the address, and we're going to modify this in such a way that we change the new address dot send adder equals s underscore 1 second dot s. What am I missing here? I think that's all right. Yeah, and that is going to be 232. We can convert this into 192.168.1.1, and I believe that, okay, my bad, these need to be commas. Okay, 192.168.1.1 and from BE bytes, I think, yes, from BE bytes. So now I've essentially overridden the IP address as 192.168.1.1. Next thing that I am going to do here is, let's see, how about we make this a sock adder. Yeah, I think this works. Sock adder 1. Cool. At this point is where the inflection comes in. We need to call the original method that is exposed by libc. So for that, we're going to go all the way up. Give me 1 second, actually. Let's just keep this here. For that, we need to bring in the method that we would call on the C library, right? So let's bring that in at the beginning. So the way we're going to do this is we are going to get the libc dynamic link. I believe it's called the dlsim. Let's check the documentation real quick. Okay, called the dlsim, I believe. Right, so this takes a handle and a symbol. So essentially you can provide it the name of any method and you're going to get a pointer to that function back. So let's use that. We've got the libc dlsim and we are going to give it a handle. A handle is essentially a way to let it know where to start looking for. So what we're going to do is we're going to call it we're going to give it the directive of rtld next. What this tells libc to do is to, in the chain that we had looked at when running the ldd command, it looks at the next library and keeps going until it finds the method that we're looking for. We're going to look for the connect method. We need to end this with a null byte. And since this has to be sent as a pointer, as a C character, so let's do that. Now at this point, we've got a pointer to the method, but we don't really know how we're going to call that method. We can't really call it right here, right? So we need to convert it into something that lets us call this method. For that, we're going to declare a type called the connect fn, and this is going to be an unsafe. We're just essentially going to copy the definition of from libc. So let's look for the connect method, and we are just going to copy all of this. That is our type. However, in here you don't need to mention the name, and all of these names can go as well. So this can go, this can go, and this can go. Great. Why is this failing? Const sock adder is failing. I guess I have to refer it this way. Or not. Give me a second here. Oh, right. I just need to get rid of this keyword here and this as well. And I can add a semicolon at the end. Great. So now we've defined the connect fn type as this particular method. So it's a method that's an integer, that takes an integer, that takes a C integer, that takes a socket address and the socket length and returns a C integer. Now, once we've got that, we have to change this pointer into this type. So how do we do that? Well, thankfully, we can let's just name this let real connect equals let's define this as connect fn equals this. Now if we take a look at the output of the return type of dlsim, it's a void pointer. That doesn't really work for us. We need to convert this into a function of type connect into the type connect fn. So for that, we've got the Rust standard libraries method called transmute, which essentially converts all of that. Let's get rid of this at the beginning, which converts the void reference that we have to the function into an actual function that we can call from Rust. Now, the crucial part here is you have to get the definition right, because any incorrect definition is going to lead to a panic at runtime. These things cannot be verified at compile time by Rust. So now that we have the real connect method that actually needs to be called, we can finally actually call that method, right? So let's do that. Let's call real connect. It's going to take what is it going to take? It's going to take the socket. So we have the socket, then we have the address. In here we're going to make it the new address and new adder. And since we've changed all of this, since the size of address must have changed, so we can get the size, I believe it's called size of var, and that is going to be new underscore addr. Let's see, create function size of var. Let me check what it was. I'm not sure. Size of value, I believe. No. Let's see. Rust size of value. Size of val. Great. Okay. So obviously all of this is going to fail. We're going to fix these errors real soon. So the first error that we're getting is the fact that it found a U size where it actually expects the socket len. So we can just cast that into socklen, I believe. Sorry, socklen. And that solves that. Now the problem here is that it expects a pointer, not really the new address. So we need to convert this into the relevant pointer. So we're going to give it the reference and convert it into const sock adder in. Again, the issue here is that since this is a sock adder in, we need to convert this further into a sock adder. So we can do that as const sock adder. Now finally we've figured everything out. We've converted the new adder into a constant to the sock adder in, and then finally to a pointer to the sock adder, and we can get rid of this. So what we've essentially done is we've overridden the address that the calling application had given us, and we've changed that to 192.168.1.1. We will have to define the port as well over here, right? Or not. I think synadder, I think we are sorted here. Sock adder in sock adder. Yeah, we are going to have to give that new adder dot syn. Let's see, sock adder needs a syn port. Let's do that. Syn port equals the old address, which was, let's get the port out over here actually. So let's define, let's do let's move this around a little bit. Give me a second. Okay, so I'm going to copy all of this. I'm going to bring it in here, and this is going to return -1 as usual. However, right here we are going to define let port. That way we can bring the port in here and in here, and finally send port equals port, and we can return right here. One more thing, I think we will have to convert this into a big Indian port, but let's take a look at that. If it works like this, it should be fine. Our build, and we've got this going for us. It's working as usual. The reason it's giving me an error over here is because I've got nothing running on port 80. So let's do a search for google.com, and oh, okay, my bad. Looks like it did not build. That's weird. It's supposed to return all of this. Okay, Cargo build release, and cool. It could not connect to port 80, most likely because yeah, I have to convert this into U32 to how do I convert this into big endian? Oh, I can just do port dot to be, I believe. Let's try this now. Right, so there's a couple things I missed. One would be that we have to convert this into big endian. Another would be that we have to define the family here, syn family. So let's do that, and let's build this again. There we go. So we've got this working. We perform a curl on google.com, and that actually leads us somewhere else entirely. And so yeah, the reason I can't work with IPv6 is because my service provider ISP does not support it. But I guess we get the gist. We've been able to arbitrarily modify the behavior of all of the things that the binary interacts with on the OS. And it's not about this. This is a very simple example, but the point of this video is not about this particular example. The point here is that you can modify pretty much anything you wish to, and you can alter the behavior. You can introduce variance in a system that would otherwise be invariant. For example, you could simulate network connectivity issues. You could simulate file permissions issues. You could simulate getting a particular timestamp. So, for example, you could, in a situation where you need to verify the time, or if you need to verify if your application works well on a leap year, you can verify all of that without actually changing your system time. So if your application depends on the system time, you can change the time just for your particular application without actually affecting your entire system. This opens up a uh, massive cache of whether it's testing, ways to perform testing, or ways to perform security management. You can check what kind of IPs an application is connecting to, what kind of files it's accessing. You could even, for example, you could perform malware analysis by mocking all of these syscalls. The possibilities are endless, and that is what this powerful thing represents. It's also something to worry about when you are building your own applications, that someone might be able to load in a dynamically linked library, and they will be able to affect everything that happens outside of your application. So you have to think from the point of view that pretty much nothing you trust from outside your binary is actually trustworthy, whether it's the network or it's even your SSL libraries if they're dynamically loaded and things like that. So anyways, I hope you found this video both informational and entertaining. If you have any questions whatsoever, feel free to reach out in the comments below. I'll try to answer them. And if you have any suggestions on the videos or any particular topics you'd like me to cover, please let me know. I've been working on learning about eBPF and all. So I hope to get to a position where I can then create videos on it. Until then, have a great rest of your day, and thanks a lot for watching. Bye bye.